Hello, everyone. Today we have Eigil Rischel from Tallinn University of Technology, who is going to be talking about triple categories of open dynamical systems. Thank you.
Good. So yes. Well, thank you for inviting me to speak. So perhaps I should start by warning everyone that I'm a computer scientist. So this will be a little bit outside the sort of the usual scope of this seminar, but I hope you'll find it interesting anyway. Um, so maybe let me start by saying sort of the problem, the pedagogical problem that I had to solve in writing this talk is that what I really wanted to bring to this seminar is a particular problem in my research that uh, you know I was able to solve. You sort of make something very complicated very simple by applying sort of some ideas from homotopy theory. Maybe I should also say when I say homotopy theory, I really just mean higher category theory. It's that sort of homotopy theory talk. There's not going to be any spaces or spectral sequences or homology groups here. So sorry about that. Um, but so before I can really talk about that, I have to kind of introduce the setting, the where the problem comes from. Because if I only talked about the solution, well, it would be maybe 10 minutes of the solution and 30 minutes of technical details, which would not be so interesting. So instead, I've elected to do maybe 30 minutes of kind of context and 10 minutes of solution instead, and hopefully that will be more interesting for everyone. Um, so the title is called Trivial Categories of Open Dynamical Systems. So before I explain what I mean by that, I'm going to start by sort of introducing this framework of open dynamical systems. Uh, so there's a kind of very general way of talking about dynamical systems that I'm going to introduce. And so these kind of naturally form a double category. And this first maybe half of the talk or so is not really covering anything that I came up with. This is all due to the work of David Myers going back to 2020. I'll give some references at the end, but yeah, sort of going back to then. So then the second half of the talk will be sort of the original stuff. Uh, I'll tell you why there should be a trivial category of open dynamical systems. Then we'll talk about like why is it actually quite hard to sort of construct a trivial category, and what even is a trivial category. Um, and then at the end, and this is sort of what becomes easy when you think about it with homotopy theory is this construction of seeing how they do form a triple category. Okay, so let's get started. So open dynamical systems. Okay. So first, let me tell you what I mean by dynamical system. So, so this is kind of a special case of the theory, but probably the one that will be most familiar to you. So by a dynamical system, I mean a smooth manifold called X equipped with a section so of the tangent bundle. So you have the tangent bundle, it's a bundle over X, and I want some smooth section. Yeah. So I mean, in the tradition of category theorists, I never tell you what kind of maps I have because it's just the right one. So when I say a section, I mean a smooth section, of course. So yeah, I mean for every point in the space, there's some tangent vector at that point. Telling you, what the derivative is supposed to be if that's the point that you're at. And so that's what a dynamical system is. If I have two things like that, two dynamical systems, say x s and y s prime, then if I have a smooth map between those manifolds, then I say it preserves the dynamics or is a morphism if this square commutes. So you have the map, this is F, the map between the manifolds, then you have those two sections, which are now going downwards because that seemed more natural. And then you have the induced map between the tangent bundles, which is the derivative. So it takes a point and a tangent vector to f of that point and the derivative of f in that direction tangent vector at f of x. And so for this map to commute, so this square to commute means that this f sort of preserves the dynamics, like preserves trajectories of the system. And in particular, a trajectory of the system is just like a path that, so, well, what do I mean by trajectory? I mean a path that satisfies the differential equation implied by this section, right? So, that's some function from some interval called gamma into our manifold, some smooth function. And it's a trajectory precisely if it's a morphism into our system X from the system on this interval where the dynamics are given by sort of dx dt equals 1, which means sort of like you have a dynamical system. The differential equation is telling you I'm always moving sort of in the positive direction along my interval at speed 1. So that's what it means for sort of like the notion of morphism between systems subsumes the notion of trajectory in this way. Okay, so yeah, so actually, I mean, it says open dynamical system at the top of the page right now, but that's what I just said is actually what I would call a closed dynamical system. So to make it open is to give it some kind of interface, some way of like interacting with other systems. So first, this is not super important, but I want to equip it with call it a readout function or maybe output function that sort of, every point in the space is associated with some output of the system. So there's some function r from x to a, and a should be another smooth manifold, and r should be a smooth function. There we go. So this is not that interesting. You can just always, I mean, you can put this on, you can always just choose, this is kind of extra data on top of what you already have. More interesting is we also want the dynamics to sort of receive some input. So instead of having a function from x to tx, I want a function, parameterized function, like from x times a bar, where a bar is some other smooth manifold, to tx. And this a bar is like parameter that determines like how the dynamics work. So this is some kind of system that's receiving some input all the time. It's like being controlled by some signal or input that it's receiving along this like from this set A. So this all seems pretty. It's not that complicated. Now I'm gonna sort of unaccountably make it more complicated by saying this can be described. Oh shit! Sorry, let me just rewrite this diagram because I edited this when I was testing out the talk and I forgot to edit it back to what it's supposed to be. So this is a map of bundles from x to a bar times a, x times, sorry about this, a bar times x, tx. There we go. Okay, so I have this on the right side here. I have just the trivial bundle of a, like, a bar times a over a. So all the fibers are a bar, and this is a trivial fiber bundle. Then I have this map, the readout map, sort of from x to a. And well, I can form the pullback of a trivial bundle by this map. I mean, there's nothing interesting going on here because it's trivial. So this is just the trivial bundle of a bar over x. And then like this section map or this dynamics map from x times a bar to tx, like the property that this is a kind of parameterized section, that it every x goes to some tx that sits over it, is precisely the fact that this triangle commutes. So, I mean, again, as I said, this is kind of making things that are not that complicated more complicated for apparently no reason. But I mean, you shouldn't be strangers to that as topologists. But you can see it like this, and yeah. So what I was saying is, if what we have, like this bundle is trivial, like if the output is just, this is the diagram I had before, the point, and if the a bar is also just a single point, so this is like point times point, which of course is just point. Then the pullback is just x, or x times point. That's the same thing. And so so R is trivial map to the terminal object, and our S becomes just a map from the kind of the trivial bundle, like the bundle where all the fibers are points, over X to Tx, which it just amounts to a section of the bundle. So if we have trivial inputs and trivial outputs, then we get this in this sense. Then we get just a closed system, right? So maybe worth noting. Let me just go back here to make this the diagram we had before. If we had there we go. If like at the right side here, I have a trivial bundle of like the inputs times the outputs over the outputs, and this thing would make sense to if I replaced this with a different bundle. So I could have the inputs kind of dependent on the outputs. And I mean, that's not super important, but it's just a generalization that I'm gonna make at this time, even though don't think too much about that. So let's keep going. So okay, so now let me just explain some random definitions. So if I have two bundles, then there's kind of two ways that I can talk about mapping between these two bundles. So first of all, what you would normally call a map of bundles is a square, a commutative square like this, where you have a smooth map in the base, a smooth map in the total spaces, and diagram commutes. I'm going to call this type of map, a chart between two bundles. Just to have a name other than map of bundles, because I'm about to say a different kind of map between bundles. So what you could also do is, well, I'm still going to ask for a map in the base, but now I'm going to pull back this bundle E prime to B over X, and then I'm going to ask for a map in the other direction from the pullback to E, like over X. And obviously, like if I had drawn this F sharp in the forwards direction, this thing would be equivalent to this thing, right? Like a map into the pullback is just a map sort of into E prime such that this can. So this is a kind of like, forwards in the base, reverse in the fibers in a certain sense type of map that we're going to call a lens. And if you sort of stare at this for a while and draw some pictures, you can convince yourself that you can compose these like without any problems. So there's a category of charts and a category of lenses. Okay, so what we've just seen before cast in this language is that a closed dynamical system is a lens from the kind of the tangent bundle to the trivial bundle of a point over point. Whereas an open dynamical system is a lens from the tangent bundle to some other bundle. And I call this the interface system. It's like telling you kind of how it can interact with other systems. And again, I'm going to get into this in a little bit more detail when we generalize, but just you can kind of convince yourself that if I have bundles like this and charts like this and lenses like this, then there is a natural notion of commutative square like this. Like it commutes in the base, and because it commutes in the base, you can kind of make sense of the square in the fibers, even though the arrows are going in different directions, and that one commutes too. And given that notion of commutative square, a map between spaces that are systems is a map of systems, like in the closed case, precisely if this square commutes. So like you have those two maps lenses to the trivial bundle that give you the dynamics. Then you have the derivative chart, because like you get a commutative square like that. That's a chart up here. Then you have the kind of equality chart down here, and that commutes. If and only if this is like this preserves the dynamics. So we can define a map of open systems to be a map like that and some chart such that we get a commutative square like this. So it's what this amounts to is like you have some map between this. Like you have state spaces of the system and some kind of mapping on the inputs and outputs such that if I'm driving these two systems with kind of corresponding inputs like that are related by this map, then I'll get kind of the same dynamics, or like the trajectory I get in X will go under the function to the trajectory I get in Y, and the output that I get in A will go to the under this function to the output trajectory that I get in B. That's kind of what this definition means. Okay, so now we have some kind of that formal setup for open dynamical systems. Or well, that wasn't formal; it was concrete. But we can make like we didn't use that many features of the category of like smooth manifolds. So the ingredients that we need here are so we have a Grothendieck fibration A to C. If you one of those people who learned category theory from higher topos theory, this is what Lurie calls a Cartesian fibration. It's like the kind of thing where the fibers here, like this gives you a functor from C up to cats, and like so the fibers vary functorially contravariantly in the objects of C. So the example that you should keep in mind is the category of like bundles and bundle maps, charts, as I called them before. Sort of mapping down to manifolds by the functor that forgets the bundle and just remembers the base manifold. And this is a fibration, a Grothendieck fibration, because a pullback of a bundle is a bundle. That's the right universal properties. So that's the first thing you need. Then you need a section of that fibration. So something that assigns to every space some bundle over that space. So for example, a tangent bundle. And that's kind of it. So the thing that we call charts are going to be the morphisms in A. The lenses are the morphisms in the fiber-wise opposite of A. Like fiber, like so you take a fibration corresponds to a function like this. I post-compose this with the sort of opposite category. Then I have another function like this, and then I can go back to a fibration. So as tuple like this, like the C, the A, and the T, and of course I haven't given a name. Like I don't give a name to this fibration. That's just kind of implicit here. I call that a dynamical systems doctrine. And everything I said so far about like dynamical systems, open dynamical systems, trajectories, all that stuff works in this generality. So there's some examples. So, well, there's this one I just explained. Here's some other examples. So if I, instead of like manifolds and bundles, I take like instead of manifolds, I have sets, and like a bundle of sets, I'm just going to take to be like an indexed family of sets. So like some other set with a function to that base set. Codomain fibration here. And then I lay it, instead of like some sort of tangent bundle, I just take the trivial bundle, like x times x over x. That's what I'm going to call the tangent bundle. Then a dynamical system, or a closed dynamical system in this situation, amounts to choosing a function from x to itself. So this is some sort of discrete dynamical system, like this function is telling me, where am I going to be on the next step. So, given some starting position in a dynamical system like this, I get a sequence of states. And the input and output is like every step my next state depends on the input that I'm receiving at this current state. So we would call this a discrete deterministic dynamical system. We could also take the same base category, so take sets, but then the sort of the morphisms between bundles are allowed to be stochastic. So I take this is the Kleisli category of the distribution monad. If you don't know what that means, don't worry about it. Like the maps are you have sets, and then you have functions, say from X to probability distributions on Y. And so this is some sort of like map that can you give a random output. And then your systems are kind of, well, there's still discrete time like the ones up here, but they're stochastic. Each step something random happens. You could also take instead of probability distributions, you could take subsets. Then you get kind of non-deterministic functions where like there's a range of possible things that can happen, but there's no like quantitative statement about which of them are more likely to happen. So yeah, those are pretty important in computer science, actually. Non-deterministic systems like that. Okay, so there's many examples like this, and you get these kind of notions of morphisms between system, and everything kind of works as you expect. I mean, maybe we've gone through this pretty clearly, so it's not completely obvious what you expect, but well, okay. Okay, now let's talk about double categories. So maybe you already know this, but I'm just going to go through it quickly. So a double category is an internal category in categories. So what does that mean? It means, so instead of a set of objects and a set of morphisms, I have a category of objects, that's this C0, and a category of morphisms. And then I have like domain, codomain, and identity functors, where like the identity functor takes the like an object to the morphism that is its identity, but that's a functor instead of just a function. And then crucially, there's a composition operation which goes from the pullback of C1 by itself over C0. So like this is kind of the category of composable pairs to C1, and then they have to satisfy some equations like associativity, unitality, but also like the domain of an identity is the object that you started with, and like the domain of a composite is the domain of the first morphism in that composite, and so on. So it's kind of important that there's also an explicit description here. So you could say, so to describe a double category, you have some objects, then you have a collection of vertical morphisms. Sometimes they're called tight morphisms. You have two different conventions, and those form a cat CV, the vertical category, with the C0 as the objects. Then you also have horizontal morphisms or loose morphisms that form this category CH, and which again have the same objects, like C0 as objects. And then you have a collection of squares. So it's given four morphisms, like two horizontal morphisms and two vertical morphisms like this, there's a set of possible squares in here, and they compose sort of in the graphical way that you would expect along their boundaries. So just to quickly give like the correspondence between these two definitions is that the vertical category in this description is the C0, like the second of these two categories that you have up here. The morphisms, like the horizontal morphisms, are the objects of the C1, the other category, and then the squares are the morphisms of C1. Morphisms of C1. And so, like, well, this explicit description makes it kind of obvious that there's a symmetry. Like, if you can swap the vertical and horizontal morphisms, you still have a double category, which is not completely clear in this kind of definition. Yeah. So that's a double category. There's a lot of examples of these. Oh, sorry. It's something called a pseudo double category, because obviously when I said the double category has to satisfy some equations, everyone says, what's some equations? Categories shouldn't satisfy equations, or like structures inside the category of categories shouldn't satisfy equations. They should only satisfy like coherent natural isomorphisms. I shouldn't ask for composition to be associative. I should only ask for it to be associative, up to some two cell that's like coherent. And of course, that's true. So somebody already wrote down how to like what the right definition is, and that's called a pseudo double category. And of course, if you want to like emphasize the distinction, you call the other one strict double categories. So let me give some examples of double categories. So if you have C, C a category, then you can define, oh, sorry, this has been a bit unclear. You can define a double category that's called C box, where the horizontal and vertical categories are both equal to C. And so I tell you what a square is, and a square is like a commutative square in C. So every square either has, like every boundary either has a single square, single element in the set of squares, or the empty set. Right. So if you have a monoidal category, you probably already know that a bicategory with one object is the same thing as a monoidal category. And this is just the double category version of that. You form a double category called BC, the D-looping of C, where the vertical category is trivial, and the horizontal like the morphisms of the horizontal category is the objects of C with tensor as the composition, and the squares are the morphisms of C. Right. So maybe a more kind of interesting example is there's a double category where the objects. Oh, hell. Sorry, my. Slides just disappeared. There we go. Does this look right for you now? Can you see the whole thing again?
Yes.
Good. Sorry about that. So there's a double category where, let me draw a bit of here. So the objects are rings. The vertical maps are sort of ring homomorphisms. Well, this R1 and R2. The horizontal maps are bimodules. So a horizontal map from R to S is like an RS bimodule. And well, okay, so the ring homomorphisms, to compose them, you obviously just compose them as functions. To compose the bimodules, you tensor them along the boundary that you're composing on. So like you have an R1 S1 bimodule and an S1 T1 bimodule. You take like tensor over S1 to get an R1 T1 bimodule. That's the composition. And the two cells are sort of homomorphisms. So if I have two bimodules like M1 and M2, then so I have an R1 S1 bimodule and an R2 S2 bimodule. I can view this one as an R1 S1 bimodule by restricting scalars along these two homomorphisms. And then I want a function from M1 to M2, which is a ring a module homomorphism for those two structures. This is actually like there's a lot to say about this double category. You can develop sort of a lot of homological algebra in this setting. It's very nice. So that's a important example. Okay, so here's some more theory. Sorry, I think I have to rush a little bit because I'm not quite on the schedule that I wanted to be on. Okay, so suppose we have a vibration like before. Then we can form a double category. It should probably have a more like formal symbolic name, but I'm just going to use what David Myers calls it, which is the double category of arenas. So the objects are the objects of A, which are like, remember from before, they're kind of bundles or something like that. So we call them arenas because they're like where the systems can interact with each other. The vertical category is going to be just the morphisms of A. So remember before I said like the vertical maps are going to be the charts, and the charts are just the sort of the maps where the both things are going in the same direction. So they're just the morphisms of A, just the maps of bundles in what you would think of as the normal form. The horizontal maps are, as I said before, the maps in the fiberwise opposite of this fibration. So now let me say what that is concretely. It's a pair where you have a map in the base, some map F from like between so I've called this fibration P. And you have a map from px to py. And then you have, so because it's a vibration, we can define some pullback functors, like for every such map in the base. So I can pull back y to be over like px, to some object over px. And then I ask for a map from that pullback to x, which of course is also over px, and it has to be in this has to be a map in the fiber of px. So this is just the definition I gave before of a lens where you take the pullback and then a backwards map, but it's like in the kind of general setting of a vibration instead of the specific setting of bundles. Okay, so now, oh, sorry, yeah. So a square commutes. So suppose I have a square. I forgot to draw the actual square of things. So if I have a, like, say x1, x2, y1, y2, and here there's a chart, and here there's a lens, and here there's a lens, and here there's a chart. I just realized I drew these the other way, like transposed in the start of the talk, but that's probably fine. Then, so what does it mean? I have to tell you what it means for something like this to commute, to define the double category. And what I'm going to take it to mean is that, so, x1, like this chart from x, that's, sorry, I was expecting this to work better. I wish it would at least just kind of keep displaying the image while but actually maybe, sorry, let me, it should be synchronized to,
You can see the entire screen again.
yes, well, now it's not streaming from my Remarkable, so now it's just like the notes, like this synchronized version on my computer. But yeah, so now you can't see that picture that I was drawing down here before. But I don't want it to keep desynchronizing, so I'm just gonna do it like this. All right, let me hurry up. So okay, so if I have a square of lenses and charts, then, well, one thing that gives me is like both a lens and a chart give you a map in the base from px to py. So that, I get a square like this, and that one has to commute. And then the other thing is, well, I have, a map from, I have a chart from y1 to y2. So that's a map from y1 to y2. I can, use this f1 and this f2 from my lenses to pull back. And because of the commutativity of this diagram, like this map is going to induce a map between the pullbacks. It's a slight calculation involved in that step, but don't worry about it. And so it's a map between the pullbacks. The lenses give me a map from these pullbacks to x1 and x2, respectively. Then, of course, the chart from x1 to x2 gives me a map from x1 to x2. And so there's a kind of reversed diagram, and I want that one to commute. And yes, so of course I've already been using these terms, but the vertical maps in the category of arenas are called charts, and the horizontal ones are called lenses. Okay, sorry. Okay, so if I have a section like I did before, then I get a double category of systems. The systems are what I said they were. They're just lenses from a tangent bundle to something. A vertical map is just, a map in the base, a chart, such that this is a commutative square in that double category. And a horizontal map is going to be a lens between the systems, such that this square commutes. So I can either go from TS to TS prime by the sort of derivative map, or I can go to A and then to A prime with these two lenses. And then, of course, I have a lens down here defining this system. And then you have A prime in both places at the right, so you can take the identity chart and ask for that. So you get a double category of systems. There's a forgetful functor from systems to the category of arenas. And this is actually, I mean, I'm not going to get into that, but this is a very nice functor. It's uh, like a vibration in one direction, sort of a lax vibration in the other. So you can like, there's a lot of really sort of nice categorical things coming out of this. Okay, so now we get to the triple category. But before we get to the triple category, I have to like explain a little bit of random stuff to motivate it. So if I'm talking about like a very simple sort of input output machine where like, every step I put in some input, it does something and then produces some output. So like, you have say the input, the set of possible inputs is A, the set of states is S, then clearly the dynamics are going to be something like, you have a function from S times A to S. Then there's kind of two ways you can define the output. So either you can say there's a function from S to B, so B is the set of outputs, where like the input that we got kind of on this time step only affects the next output. Or we can say there's a function from S times A to B, and like the input that we got on this step goes directly through to the output if we want. The distinction between these two kind of ways of thinking about a kind of input output machine actually goes all the way back to like when people were designing circuits in like the 50s and I think, don't quote me on the year, but like, when you're designing like a circuit to compute some function with like state inside it, it matters whether you like these electrical signals pass directly through or whether you kind of only get an output on the next tick of the system clock. To give a kind of more theoretical motivation for the difference, these ones, the Mealy machines, allow you to have, so these are called Moore machines, these are called Mealy machines. These ones allow you to have a kind of identity system that just passes the input directly through to the output if A and B are the same. These ones give you a kind of traced category, if you know about like traced monoidal categories, where you can feed the output directly into the input without creating some sort of like undefined feedback loop. So there's two different ones. The ones that the machines that we've been looking at so far are kind of more like machines because we have a function here that gives the output just as a function of the input. And in fact, in general, of the state. And the input is kind of fibered over the output in a way that makes it impossible to like the output couldn't possibly depend on the input because we can't even say what the possible input sort of things are before we produce the output. This is how our machines look so far. Now, a way of setting up a Mealy machine like dynamical system would be to say, well, like look at a function like this. So I'm gonna take a S times B, where B is this input space. Then I'm gonna just form the trivial bundle and have a map to like the tangent bundle times this like A times B. So now it's the trivial bundle of A's over B's to this bundle. So it's like I know where I am and I know the input and I produce like a tangent vector and an output. Okay, so suppose our vibration is actually a monoidal vibration. If you don't know what that is, don't worry. And suppose that our section is actually a monoidal functor. Then the double category of arenas becomes a monoidal double category, which means exactly what it looks like it should mean. Then a Mealy machine can be defined as, so you have like a state space, an interface, but now you ask for a function, or a lens from the tangent bundle tensor A to the unit arena. So for example, in the case of like smooth bundles, it's like you have a some bundle like A times B over A times B over A times S over TS over S looks like this. The map to the unit is trivial, and the pullback is just kind of the bundle of points, and then this map is like just the thing we discussed before. So this kind of looks right. The main difference, or like the main interesting thing, is that now the thing in the base is the set of inputs, and the thing in the fiber is the set of outputs produced by the machine. Um, okay, so these look nice. This is a good definition. You can kind of do all the stuff that we just did for more machines, for Mealy machines as well. It's kind of obvious idea when you look at those definitions is to like form a common generalization where you say, now I'm going to form a bi-machine or whatever you want to call it, where there's two interfaces, A and B, and a machine of that form is, so you have a state space and you have like a map from T as tensor A, a lens from T as tensor A to B. And so of course, if this is like if B is the unit, this is a Mealy machine. If we take A to be the unit instead, this is a Moore machine, or like up to isomorphism. And since T is a monoidal functor, we can compose these. So if I have something like this and something like this, then I form a thing where the state space is S prime tensor S, and it's going to go like the left interface is going to be A, and the right interface is going to be C. And like you use this formula to compose it. It's kind of obvious how this works. And this is like associative because monoidal categories are associative and unital. So it looks like there's now a triple category of systems because there's systems as morphisms, there's lenses between the systems and charts between the systems. Wow. Okay. So we have a kind of weak or pseudo triple category on our hands. And the reason it's somewhat pseudo is because, of course, the monoidal structure might not be strict. And there are some reasons why you kind of don't want to just assume that it's strict, even though in many cases you can. So as you know, as homotopy theorists, it's very hard to construct like a higher categorical structure by hand. And like 3 is about the limits. You can kind of construct monoidal categories by hand, but after that, it's impossible. I mean, of course, okay, in your work, maybe it's mostly infinity categories, which you literally can't, like must have some systematic way of constructing the higher levels. But it's very fiddly to do these kind of things by hand. There are definitions of like pseudo triple categories, they're called intercategories. They're actually quite a bit weaker than what I need. But they're, it's a very complicated set of axioms, and it would be hard to know, even if you proved that you had constructed a triple category, that you had kind of the right sort of thing or to do anything with it. So it would be nice to have a more systematic approach, both to defining what is a triple category, understanding that, and also to constructing them. Okay, so categories are like the concept of category limit theory. That is to say, there's some small category and some class of cones in K, such that internal categories are just functors that take those cones to limits. So it's like like concretely, you can take like simplicial objects where all of these diagrams go to pullbacks. So that's like, I mean, you guys probably know about Siegel objects since you're homotopy theorists. This is like a Siegel. So a double category is a Siegel object in categories. So the idea is to put like infinity in front of all the words in this page. So there's an infinity category of one categories. And by infinity category, I just mean like infinity one category. So like, it's categories, functors, and natural isomorphisms. And then the higher levels are kind of truncated. So this is a 2-1 category. So I take, models are, like simplicial categories where those diagrams from before go to homotopy limits, infinity limits. So this should give me some notion of pseudo double categories. So and then if I do it again, I should get some notion of pseudo triple categories. So that's quite nice. I have a monoidal. So suppose we accept that that's a good definition of pseudo triple category. So if I have a monoidal category M that acts on the normal any other category D, then there's a double category of parameterized morphisms where the vertical morphisms are the morphisms of D, the objects are the objects of D, and the horizontals are parameterized morphisms like this. So like M, like a morphism from X to Y horizontally is some object M in M and a map in D from M acting on X to Y. And then there's, some notion of squares, commutative squares. And this is kind of what we want. Like this looks like the right idea. Um, so there's a functor from the category of like monoidal actions to the category of pseudo double categories. So this para. So now I need to cook up a pseudo category internal to this category of actions. So suppose I have one of these monoidal doctrines of dynamical systems. Um, so okay, so for a reason that I won't get into, you can if this is symmetric monoidal, you can just replace the category of actions with the category of morphisms in symmetric monoidal categories, like a symmetric monoidal category acting kind of coherently on another symmetric monoidal category is just a strong symmetric monoidal functor. Same way, like a monoidal, like a commutative ring acting on a algebra is always just like a map into the core, if you know about that sort of thing. So that means I just need to cook up like a category internal to morphisms of symmetric monoidal categories, which is just some sort of like I just need some sort of diagram of the right type. So it's this one. So on the in the domain of these morphisms, we have a category in symmetric monoidal categories, which is a double category. It's so the base category is the category of isomorphisms in C, so the core of C, which goes to, so this is like the category of arenas but transposed. So the lenses are in the base now, and the charts are in arena in the secondary part. So yeah, so C acts on charts, which is not what I want. But C doesn't act on lenses because like this function, like T goes to A, not to a fiberwise opposite. But if I just look at the isomorphisms, those all like an isomorphism chart is always also a lens, so that's fine. So you have this action, and then so like para of this thing is like the parameterized morphisms of this form are exactly those like sort of systems of like of this type that we looked at before. Like you have some S, and then like the way that it acts is like T as tensor A, and then you have a map from that to B, and the map here is a lens. And then the double category is like, so then you have like the category of so this is like arrows in C, so not all of the arrows, but those are the objects, and then the morphisms are the isomorphisms. So this has, I mean, that's a category over this. And here we just have the rest of the category of arenas, and you can kind of see that this extends here. And then you stare at it for a while, you realize, so first of all, you show that this is actually an internal category that's kind of mechanical. Then you see that this para construction preserves like homotopy limits, infinity limits, or two, whatever you want to call them. So it takes a category in this category of monoidal actions to a category in the category of double categories, which is what we've decided the triple category is supposed to be. So this gives us what we want almost. So the only problem is that like models, like what the thing, Siegel categories are not the same thing as pseudo double categories. So we're almost out of time. So let me just kind of blaze through this. So there's a problem with strictification, which you can solve. First of all, like just up to equivalence, and everything can be like strictified. And also the thing, like if you look at the way that our construction works, it actually produces something that is strict. So, but what I mean by this is like a pseudo double category still has strictly defined composition, and still has like strictly like the domain of the unit morphism is equal to the object you started with, not just isomorphic. So this is not really a problem. Then the other problem is that like if you have a kind of Siegel category, then your composition is defined when the codomain of one morphism is just isomorphic in the vertical category to the domain of the other morphism, which is kind of too strong. You have too many compositions. So it turns out that this is a kind of, well, like Siegel categories are just a subset of pseudo double categories, but like a full subcategory kind of subset. So that it's just a property to have these extra compositions, and we can kind of describe what that property is like. And I mean, that also means that we don't really have to care because we're constructing something that's just stronger than what we wanted to start with. So that's fine. And also we kind of understand what the extra structure that we get is. Okay, I think, yes, I'm out of time now. And that was time, well, by running at the end, we managed to get the timing right. Thank you for listening to my ranting. On the screen right now are some papers that are kind of relevant that you can already read on the internet. At some point in the future, you'll be able to read this in my thesis, but it doesn't exist yet.
Thank you very much. Great talk.